Welcome to the last technical session of the day. So the first talk is given by Professor Biplab from Uppsala University, Sweden. And he is going to talk about complex magnetism in high temperature two-dimensional magnets.
Thank you, Srimanta. Thanks to all the organizers for the invitation. I am going to continue with the 2D magnetism, but not from an experimental point of view, but from the theory and computation. I will use some ab initio tools to tell you a story about some two-dimensional metallic ferromagnets which are in focus now. Let me first acknowledge my collaborators, my present students, PhD students. Two of them are here. Then my present postdoc and my former postdoc, Duo Wang. He finished his PhD in 2022. And I have a lot of collaborations with the experimental group of Soroj Das in Chalmers in Sweden. Bing Zhao is very instrumental there, senior researcher. Then in my division, I have got a lot of help from Vladislav and Yaroslav, who are active collaborators. I don't have to, thanks to Professor Shurudi Shah, I don't have to say much about 2D magnetism because this has already been told, but just want to focus that these van der Waals heterostructures give us a lot of possibilities. They are very weakly bonded, layers are weakly bonded, and we can bring different types of two-dimensional layers to expect to get some unusual exotic properties. New addition, two-dimensional magnetism, a few years old only, magnetic long-range order in atomically thin materials. That's the key word actually. And we all also heard about Marvin-Wagner theorem. I don't have to repeat that. Magnetic anisotropy is the key thing here. So all these systems where we see even down to a monolayer where we see a magnetic long-range order, the magnetic anisotropy plays an important role. So if you look into this plot, you will see that there are several two-dimensional magnets which are listed here. The normalized TC as a function of number of layers, you see that even in a monolayer regime, you see non-zero. And chromium I3 is one of the first ones, a ferromagnetic insulator, very interesting system, but its Curie temperature is rather low, around 45 Kelvin in the monolayer regime. So not of much use so far, but I will talk about some metallic ferromagnets, iron germanium telluride class, which has a very high Curie temperature. Anyway, this is a bunch of materials have been listed here. Some of them are in bold, ferromagnetic, strong magnetic anisotropy energy, some TCs and blah, blah. So there are many such materials which are coming up nowadays. And some of them, most of them are ferromagnetic, some are antiferromagnetic, some are even non-collinear, which is even more interesting. Why 2D magnets are so important? This has also been told. Magnetic tunnel junctions, spin orbit torques, which are all, just name it. There are so many twistronics. All these things are very important nowadays. Important thing, this was also mentioned in that talk, which is very interesting, that how do we engineer an interface of 2D materials? This is very interesting. You can have several processes, charge transfer or hybridization, strain, spin orbit coupling was mentioned, proximity effect due to a strong spin orbit coupling material. Dielectric screening is also important. 2D materials, their screening is rather poor outside the material. So things like that, there are many such avenues there by which you can control the properties of a 2D magnet by bringing another 2D material close to it. So basically then I can come to a bunch of questions, general questions that one, being a theoretician, one can ask actually, that how do we obtain accurate electronic structure and also the structure of the materials, the geometries of the materials. The next question is that, what is the importance of many-body interactions here? These are mostly materials I will be talking about. These are 3D transition metal elements based materials where we know that these are narrow 3D bands. electron correlation is important. Then the next question comes that how do we obtain accurately the interatomic exchange parameters? Because these exchange parameters with different flavors, they control the magnetic properties of these systems. Another interesting question one can ask whether there is a topological feature in the magnetic properties of the system. For example, in Magnon spectra, are there topological features? We heard about topological features in electronic dispersion, but in magnonic dispersion, whether there are some things. I'm not going to talk about this, but this is also a hot topic. This I already said, that how to control the properties by proximity effects. Then when it comes to spin transport, what are the characteristic features of spin transport? When spin polarized electrons pass through these 2D magnets, or even they get spin polarized by passing through these 2D magnets, what happens? And finally, last but not the least, can we find new materials, 2D magnets by high throughput calculations? So my plan for today is to talk mostly about this family of compounds, iron germanium telluride, iron 5 germanium telluride. This is the system which is least understood. Iron 3 germanium telluride has been, there are many papers on this, but there are many controversies regarding this system. So I will talk about this one. I will put an emphasis on the role of dynamic electron correlation in this family of compounds. Then there are some specific systems, doped systems with cobalt doping and nickel doping. I will talk a bit about that. And if there is time, I will show you some spin transport characteristic features through iron 4 germanium telluride, which is also very important. So I want to do a little bit of advertisement that we are developing an automated platform for high throughput DFT calculations. The basic objective is to screen or many materials, or to find new materials, and finally to come up with a few very important materials. And we can start by different ways, but one of the ways that we also do that, we take some chemical elements and mix them with some chemical composition, and then we do some evolutionary structure search algorithm to find the best possible structures, and then we see whether this is magnetic or not, and after that, yes or no, it doesn't matter. We check the stability by different means, stability of these systems, and if it is stable, then we go for the characterization. If it is not stable, they are discarded. So in the characterization part, you have the electronic, topological, magnetic, and many such characterizations. And the main point is that all these things will be done in an automated way. So no human intervention is needed. So to be more specific here, I mean, stability checking, who are in this DFT field, when you will see that we check stability by different means. All of these checks are done. Electronic properties, different types of electronics properties are studied. Even the extraction of tight binding Hamiltonian from DFT, then lattice properties, mechanical properties, and for today's talk, magnetic properties, magnetocrystalline anisotropy energy, interatomic exchange parameters, then the possibility of spin spirals and things like that, Monte Carlo simulations, then spin texture and skyrmionics. All these things, they are included. The things that are light in color, they are being developed now. All this dark color, they are already developed. And the different softwares are used for this. So basically, theoretical methods that I'm going to use today, the heart of everything is density functional theory. And I already told about the electron correlations. Either we use, in some cases, DFT plus U in a static mean field way, or we use a dynamical correlation in the flavor of dynamical mean field theory. The interatomic exchange interaction parameters, they are calculated with this formula LKAG. These are the names of 4 authors. 1987, they wrote down this formula many years back, and based on a Heisenberg model. So basically a Heisenberg spin model can have this kind of this kind of terms. Actually, this is an isotropic term. This is an antisymmetric Zaleshinsky-Moria interaction. This is the magnetic anisotropy, single line magnetic anisotropy. If you wish, you can add more terms in the spin Hamiltonian. And the good thing is that with our technologies, we can calculate the parameters of these terms in the Hamiltonian. That gives us an authenticity in the materials properties. All these are calculated on the basis of Green's function with multiple scattering approach and things like that. But this is the isotropic part is simply, this is a very well known formula for many, many years. Then you can generalize this formula to extract the full exchange tensor, 3x3 tensor, when you use include the relativistic effect with spin orbit coupling. Then you can also calculate the off-diagonal element of this exchange tensor, which are important for extracting the Zaleshinsky-Moria interaction parameters. And also at the same time, if you want to include the dynamical correlation effect, so this formula gives you the XY component of this exchange tensor, where you see that you have self energies popping up here. These self energies come due to the dynamical correlation effects, which is a function of some Matsubara frequencies. Anyway, this formula is the most general formula that is used to calculate the full exchange tensor within dynamical mean field theory. Magnetocrystalline anisotropy energy is as a quantity which has to be calculated with utmost importance and care, because this is very small compared to the exchange interactions. This number is very small, so one has to be very careful in finding this number. Then when you know all these parameters of the Hamiltonian, you go to Monte Carlo simulations and you go for obtaining the critical temperatures or the spin textures, magnetic textures at different temperatures, what people usually do. Coming to the systems, iron N-X germanium telluride, N can be 3, 4, and 5. Minus X because people usually observe there is some iron vacancies always present in the system. And this is a known fact, but still this has not been systematically studied as how the properties actually change with the concentration of iron. This is something one needs to do it. Anyway, the material looks like this. So this is a bulk structure. You see the bulk unit self when it is N equal to 3, Fe3 germanium telluride, metallic ferromagnet in bulk. Tc is 207 Kelvin. In the monolayer, it's pretty high Curie temperature, 130 Kelvin. So you see that if you look into this one, you see that the green atoms are tellurium atoms. They are basically on the outermost layer. Then you have iron atoms, and then in the middle, they have germanium atoms. If you go to the N equal to 5, which is a little bit more complicated actually, you see, as usual, the tellurium atoms in the upper side and the lower side. This is just a monolayer is drawn here. Then you see that this iron 1, what I call it, the sublattice iron 1, has a split occupation site. It is iron 1A and iron 1B. One is in the upper side, one is in the lower side. So iron 1 sublattice has a split occupation. This has also been observed in some experiments. So that's why it has some importance here. And then iron 2 sublattice, iron 3, and all these other iron atoms pop in, and then these germanium atoms come in between. If this paper, they have summarized the results for iron 3, iron 4, and iron 5. This is the saturation magnetization versus Tc. So obviously the saturation magnetization increases. Tc increases when you increase the concentration of iron. The magnetic anisotropy parameter that decreases, that is also understood when it becomes thinner. I mean, it has the highest value, then it decreases. What is intriguing is actually the magnetization versus temperature plot, which is, sorry, this should be Fe4 and Fe5, not Fe3. Fe4 and Fe5, you see there's a peculiar behavior of magnetization versus temperature. So at low temperature, you have a rather low magnetization, then it pops up, and then there are some characteristic temperatures you can see. And then finally, after T1, it goes to the paramagnetic state. Now, this behavior is not, as far as I know, this has not been understood properly. Why the low temperature behavior is like this? People have conjectured that there can be some helimagnetic order, complex magnetism, things like that. So this part is still under open discussions. Let's look into in more detail about iron 5 germanium telluride. Now I said that this iron 1 sublattice has split occupation. So that's why it is split, it is shown as these shaded areas. They can stay here or they can stay here. So depending on, actually in experiments, in STM studies and other studies, people have seen that there are two scenarios. One is the split occupation scenario, and one is also a scenario where all the iron 1 atoms, they are on the upper side or in one side. So let's call these let's give a name to them, structural models UUU and UDU. What does it mean? First of all, in experimental STM, people have seen a √3 by √3 superstructure rotated by 30 degrees. That basically means in the unit cell, there are 3 iron atoms in each atomic plane, √3 by √3. So that's why these UUU and UDU, 3 such letters appear, meaning that all the 3 iron atoms, when they are in the upper plane, we can call it UUU. They can be also in the down plane, we can call them DDD, doesn't matter, they're equivalent. Or there can be another scenario where there's a split occupation. Some of them are in the upper layer, some of them in the down layer. And why should we bother about that? We have to bother about that because there is a strong consequence of this structural arrangement on the magnetic properties. If you take these two structural models, do DFT, simple-minded DFT calculations, and you will see that the UDU has a little bit of lower energy compared to the UUU structure, around 0.3 electron volts per unit cell. Also, what we have seen that if you calculate the iron vacancy formation energies, you see that in the UUU structure, when all the iron atoms in the upper layer, you have a spontaneous formation of iron vacancy. That means that is not so much stable. So some of the iron atoms, they try to go away from there. And also we have calculated the vacancy diffusion barrier. So you can see that the diffusion barrier for iron 1 here is actually very small, only 36 milli-electron volt. That means when the iron atoms, they are removed from UUU structure, they can diffuse very easily and they can go somewhere else. So that makes the system rather complicated. Now, we have simulated STM images for these two structural models. So if you look into the structure, you see that these white blobs here, they are not really circular. They are kind of oblate. They have oblate shape compared to the UUU structure. So these states, they pop up because of the tellurium P states. The tellurium states, they're on the outermost layer. So they come from the tellurium P states. And you see really this non-circular type of shape for UDU structure. And this is also seen in STM. Both of them are seen in STM. When they scan different parts of the sample, they see different types of things. So this is also another signature. This oblate structure appears because when you have a UDU structure, one of the iron atoms is missing there, and that's why the tellurium atoms, they come closer and they make a trimer. And this trimerization is the reason why these white-shaped objects are not really circular there. They are oblate, whereas in the UUU, no such thing happens, no trimerization, and everything looks pretty symmetric. This is rather a busy plot. So I said that now I will only show you here the isotropic exchange interaction parameters. The convention is that the positive numbers, they indicate ferromagnetic interactions. The negative numbers indicate antiferromagnetic interaction between a pair of magnetic moments, between a pair of iron atoms. And there are so many sublattices. So if you look into this one here, the sublattice, the central site is one iron atom in the iron 1 up sublattice, okay? And then with that atom, the different pairs of atoms, they have been considered and the exchange parameters have been calculated for there. So many of them have ferromagnetic character, but you also see that some of them have antiferromagnetic character, specifically these orange ones, which are basically the exchange interaction, which is antiferromagnetic exchange interaction in the plane of the iron 1 sublattice. So this is something that we are looking for, because we are looking for some frustration in the exchange interactions where the simultaneous presence of ferromagnetism and antiferromagnetism is present. That's why these antiferromagnetic exchange interactions are very important for us. If you take another sublattice I equal to 5, you would see mostly ferromagnetic interactions. Okay. Now, when you take all these interaction parameters and you do Monte Carlo simulations, then you can plot the sublattice magnetization as a function of temperature. And then you see that different sublattices, they are here, for example, iron 4, iron 2, they are degenerate here, and these two are degenerate. But you see the little bit unusual behavior is seen for the iron 1 up sublattice, which doesn't look like a real ferromagnetic interaction. So when we saw that, we were interested to see that what is the magnetic structure for that sublattice at a very low temperature. And then basically we looked into the spins and measured the canting angles from the easy axis of magnetization, which is out of plane. So this is what you see, the histogram that you see for the iron 1, the magnetic moments which are residing in the iron 1 up sublattice. If you measure the canting angle from the positive Z axis, which is the easy axis of magnetization, you see there is a peak around 40 degrees of canting. If you go to another sublattice, iron 5 sublattice, which shows a more or less usual M versus T behavior, you see that the canting angle is rather small, around 10-12 degrees. So what does it tell us? It tells us that at low temperature, this system has a bit complicated magnetic structures. So, and it is very much dependent on the sublattice, iron sublattice that we are talking about. And iron 1 sublattice is a very special case where you have a large canting angle compared to the other sublattices. So that basically means at low temperature, you can expect to see some complicated things. But I must say that we could not reproduce the experimental feature, that a peculiar M versus T behavior that we could not reproduce. Our magnetization versus temperature looks like that. That basically means there are much more things happening there, which we haven't considered at all. Then we thought that, okay, that was a pure DFT study, the first study, because it's very difficult to do dynamical mean field theory calculations for this system. Then we thought that nevertheless, we try to do that for Fe3, Fe4, and Fe5 system. And for all these systems, we did a systematic study of the electronic structure, exchange interactions, and corresponding TCs and things like that. So first of all, when you do a dynamical mean field, okay, the other thing I must say that in literature, you will see that some people have said that DFT plus U method can be okay for this system. But we had some doubts, and we did a systematic study of DFT, DFT plus U, and DFT plus DMFT calculations to see that what's going on, which one gives us a good one. But to do that, to do either DFT plus U or DFT plus DMFT, you need some values of U that have to be incorporated. So then we calculated the effective U from constraint DFT calculations. So you see that the corresponding numbers, calculated values are there. So you see they're site dependent also, because there are two equivalent iron atoms in the Fe3, another one is separate. So you see that there are site dependent U. If you go to the Fe5, you see that they are very much actually site dependent U. So that means it's not a good idea to just take one value of U and put it for all the iron atoms. So if you take all these U values and then if you calculate the spin moments, There is a comparison between DFT, DFT plus U and DMFT, and some experimental results are here. So if you look into this, Fe3 germanium telluride, so you see that the DMFT yields 2.12 spin. These are all spin moments, by the way. 2.12 Bohr magneton. DFT is also not bad, but the DFT plus U is actually rather large. It really does not fit with the experimental results which are given here. Then Fe4 GeT2 also a similar picture is there. Fe5 GeT2 is also, you see that DFT plus U always it is giving a very large estimation of the spin moments. Not only that, if you calculate the geometry of that, so the geometrical parameters also come out to be inaccurate compared to the experimentally reported geometries. So that's why we can say that DFT plus U is not the choice of method for these metallic ferromagnets. I will not spend much time here. There's a lot of plots here, many things to say, but we see that these are all calculated within dynamical mean field theory. You see lots of antiferromagnetic exchange interactions happening. So basically, if you compare DFT and DMFT, then you'll see that there is a renormalization of the exchange parameters that is happening. If I want to summarize in one line, interesting thing is the Zhalushensky-Moria interaction parameters that can also be calculated, as I said, as a function of distance between these atoms. And in this case, this interfacial DMI can be easily calculated also in this way. So what you see that sometimes you see that there are non-zero values of these Zhalushensky-Moria interaction parameters. You will only expect non-zero values when there is a inversion symmetry that is broken. Yeah, and then you see that there are locally between a pair of magnetic moments inversion symmetry is broken. That's why you get a non-zero value of Dij. But when you add them globally, we have seen that they cancel each other. Specifically, this D11, you see these up and down arrows. These are all vectors. So up and down arrows are there. So if you sum them up, they will give you zero contribution to the DMI effect. Overall DMI effect is zero. I don't have much. Let me come here. So basically, this is a comparison between different methods. I said that there is the GIJs I talked about, the magnetic anisotropy energies. Let's look into this plot here. These are calculated TCs with DMFT, DFT, and DFT plus U. Obviously, DFT gives you a very much overestimation of the Curie temperature here. And the DMFT gives you the values which are more or less close to the experiments. They're much more renormalized. They have much better agreement with the experiments, and then we can conclude from here that maybe DMFT will be a choice, if possible, to look into these itinerant, not itinerant and localized ferromagnets. I should not call it purely itinerant ferromagnet. Quickly going through, how much time do I have? It's 11 minutes. Is that speaking time? Okay, good. So now the cobalt, now our experimental collaborators, Shoroj and his team, they came with some results. They say that if you dope cobalt into this system, 15% cobalt, you see that there's an in-plane anisotropy. So from the out-of-plane anisotropy, it goes to an in-plane anisotropy if you dope with cobalt. Then they asked for some help. And what we did, the first thing is that we need to figure out if you dope cobalt into this system, where do these cobalt atoms go? So we figured out that the formation energy of this cobalt, like cobalt sitting in the iron split site, iron 1 up site is much more than any other site. So in conclusion, when cobalt atoms are being doped into the system, they prefer to go to the outermost iron 1 layer. So they can be in the upper layer or the down layer, but they want to occupy those sites first, and then they go to the other sites. This is the first important information. And this is also when we studied the nickel doping also, it happens in the same way. We have the same conclusion that the iron 1 sublattice is first they get affected by the cobalt or nickel doping. Then we calculated the magnetic anisotropy here, the magnetocrystalline anisotropy coming from the spin orbit coupling. The plus means it's a out of plane, minus is in plane, the convention. So if you do not have cobalt here, a pristine system, it is out of plane anisotropy as expected. But when you start to dope a little bit of cobalt here, 6.7, 13 or 20%, these three compositions we could do, you see that they have changed to negative numbers. That means the out of plane anisotropy has become an in plane anisotropy. We wanted to find out the reason for that, and that's why what we calculated is atom projected magnetocrystalline anisotropy. So this is the result for the pristine system, and this is for a 20% cobalt dope system. You see that these positive and negative numbers, these are, so overall this gives you an out of plane. If you sum them up, it gives you out of plane easy axis of magnetization. But when you dope cobalt, this, for example, this iron D site here, when it is replaced by cobalt here, it instead of positive, it goes to a negative direction. So it shows that cobalt doped at this site has an in plane anisotropy. Not only that, you see that these values, they are increased here, and then this is also replaced by the cobalt up atom. You see that instead of positive, it becomes negative. So basically now with these, from looking into these things, one can actually find out that why, when due to cobalt doping, the system wants to have an in-plane magnetization because of this particular substitution of cobalt atoms. And then one can go to even more detail by looking into this heat map of the orbital composition of this, but I am not going into those details. When it comes to nickel doping, a few years back, there was a Ramesh Ramamurthy's group, they published this paper. They showed that if you dope nickel, what happens is that the TC increases with the nickel doping concentration and then it decreases. It's a peculiar feature actually, which is not easy to understand. And also they reported some kind of chemical inhomogeneity, saying that, okay, that different parts of the sample, they have iron rich or nickel rich parts, and quite complicated system. Nevertheless, we wanted to have a systematic study of this as a function of nickel doping. So once again, what we found is that, I mean, if you look into this plot here, probability of nickel occupation, the iron 1U has the highest probability of nickel occupation, and then the probability decreases here. There's certain kind of rumpling in the structure. These are details. Magnetic moment goes down as a function of nickel concentration, more or less a similar observation in experiment. The behavior of magnetocrystalline anisotropy as a function of nickel concentration, we still do not understand. This is very weird behavior it has. And the important thing is actually the calculated TC as a function of nickel concentration. So you see that it happens to be like that we also have a similar behavior. So with smaller nickel doping, the TC increases, and for up to certain concentration of nickel, then it decreases. And then we wanted to find out, and in our simulation, we do not have any chemical inhomogeneity, nothing. We just have simple-minded calculations, but these are also DMFT calculations, but still we do not have the possibility of considering clustering or phase separation in our simulation. Nevertheless, we see this kind of behavior, and we looked into the exchange interaction parameters, and we see that there are specific exchange interaction parameters, specific pairs, iron 5, iron 4 pair, they show this kind of behavior. And we can conclude that maybe it is happening because of that. The TC is, behavior of TC is controlled by this, because it has also the highest value of the exchange interaction. There are some topological consider. I mean, we looked into the spectral function. There are some peculiar features, but there's no time to discuss these things. I quickly show you, I skip this part. I quickly show you some spin transport stuff, and that will be in the last 4 minutes. Basically what we wanted to do, we wanted to see that if you drive a current through these 2D magnets, what do we expect to see? For this, we have used a Landauer-Buttiker formula. You have a source, drain, you have the scattering part here. The lead is bringing electrons. It goes to the scattering part, and then it is collected on the other side. So what we wanted is that our scattering part has iron 4 germanium telluride 2. This is a 2-dimensional magnet. And also what as an electrode, we also wanted to have a van der Waals electrode. This is an unusual setup, but we wanted to see that if you use van der Waals electrode, not simple metallic electrode like copper or gold, something like that, what happens to our transmission, spin polarized transmission. And also, fortunately, the lattice parameters of platinum ditelluride, which is a van der Waals system, that matches very nicely with the iron 4 germanium telluride system. You see that the lattice parameters are very close to each other. And these are the band structures, what you see, details once again. But this is basically the setup. You have the scattering part here, magnetic system. You have this platinum ditelluride leads. You can see a more fancy picture here. So basically what is calculated is the spin polarized transmission. So spin polarized transmission is, you see that the spin up has a, at Fermi level, at a zero bias, you have the spin up, which is a very high value compared to the spin down. And that's why you can expect the spin polarization of the current can be quite high. It is not 100% for a monolayer, but if you use a bilayer, it is nearly 100%, 97% spin polarization that you see. And then comes the important question that everybody is talking about, the magnetic tunnel junction. What about the TMR, tunneling magnetoresistance? For the tunneling magnetoresistance, what you need a tunnel barrier in between the magnetic parts. Basically, a semiconductor, insulator, or vacuum you need. So we found out that there is a material, gallium telluride, which is also a layered material semiconductor, which has lattice parameter very close to this. And we have used this as a tunnel barrier in between. And then basically what you do, you have two magnetic layers here. When in one case you align them in the same direction, magnetization in the same direction, you calculate the transmission, and in the other case you can do it in the opposite direction and then also calculate the transmission. So what you see here, this is the spin polarized transmission for the parallel and anti-parallel arrangement. So you see that the spin polarized transmission for the spin up is very high, spin down is almost zero here, whereas for the anti-parallel, they are very close to each other. So now this is okay, but then the actual point, the quantity of interest is actually the tunneling magnetoresistance. For that, you need to calculate the current. You turn on the bias voltage and you calculate the current for both spin channels and for the both configurations, parallel and anti-parallel configurations. And that is how the currents look like in these two configurations. And from there, you can calculate the tunneling magnetoresistance. And as a function of bias voltage, you see that it goes down, but at a very low bias, the value is rather high, close to 500% TMR. So it looks promising, but I don't know whether it will be feasible in experiment or not. Let me summarize. Iron 5 germanium telluride is a complicated system. Actually, the whole family is quite complicated. Iron 5 germanium telluride is more complicated. There are iron vacancies which move around, and also the different structural arrangements can give rise to different magnetic interactions and magnetic structures also. We conclude that DMFT will be the method of choice for these metallic ferromagnets. For cobalt doping in plane anisotropy, we could explain by atom resolved magnetocrystalline anisotropy energies. For nickel doping, we could reproduce this peculiar behavior of TC as a function of nickel concentration. And finally, a TMR percentage of 500%, around 500% TMR at a low bias was observed for this particular van der Waals heterostructure. Thank you very much.
I have a couple of questions.
I was quite surprised to see that your K effective, which is the magnetoanisotropy constant, has a temperature dependence. The contribution from, you showed one with the K effective was changing.
Yeah.
So why does that change with temperature? I mean,
Was that temperature or it was?
I thought it was temperature, sorry.
Let me go. No, it is not temperature. It is a TC is also plotted there. So basically, it's not a temperature dependence. It's individual values of the
Different
K
materials.
effective
Sorry.
and the TCs, individual TCs.
Yeah, so I was interested in this room temperature ferromagnetism in some of the FGT structures on doping. So how do you account for doping in these calculations? The external gating part, how is that included in these calculations?
We do it in a very simple minded pictures where millions of people do. We just replace iron by cobalt or nickel, and in various sites, all the possible sites which are in the unit cell, and then we calculate
But the doping by applying a gate field, gate electric field.
Oh, gate, no. This is real replacing substitutional doping that okay, you are talking about gating effect.
Yeah.
Yeah, gating effect that can be also done, simulated in our simulation, but that is, you need to shift the Fermi level in simple minded. Huh? This is metallic. Yeah,
No, ionic doping, people have seen that.
with the gating effect, yeah, but then they apply an electric field. Basically, it means that you shift the Fermi level with the electron doping or hole doping. You shift towards right or towards left. It is rather simple thing.
So how is that affecting this exchange interaction and the spins at each ion?
So here we have explicitly replaced iron by cobalt and nickel. So this is not really a gating effect. And that basically, that changes the exchange interaction parameters, definitely. Is iron-iron exchange interaction is the most common thing, but when you dope with nickel or cobalt, you have iron, nickel, cobalt, iron, nickel, nickel, and iron. 3 different exchange interactions. So definitely iron-iron exchange interactions are getting modified in the presence of nickel or cobalt, for sure.
Thanks for this very nice talk. I had a very simple question regarding on nickel and iron. Now, the good old GMR people, they also used to dose cobalt and nickel, and they found miscibility problems, right? So my question is, did you do the spin resolved up majority and the minority calculations for this? Because when you go up and then you go down, so is there a change in the spin majority and the spin minority, the proportions of that? And does it quench and goes?
In what?
In the iron nickel, the one that you
Yes,
showed.
but in what property?
In the electronic properties.
Spin polarization.
Spin polarization
example,
calculations.
spin polarization. We did not explicitly look into that, but that is definitely, it's a spin dependence is there.
Yeah.
That is, that's a good point. Maybe we should plot and see how it looks like.
Maybe it also reverses.
It can reverse also. At certain concentration, it may reverse. It is highly relevant to the transport stuff, so yes. But we did not look into that.
Any more questions?
Why did I say that? You were saying, okay. Because without that, you are in the loophole of Marmin-Wagner theorem, and you do not expect to see, you need to break that isotropy in the Hamiltonian in order to get a long-range order in 2 dimensions. So that's why magnetic anisotropy is very important, which breaks this isotropy. And the strength of the magnetic anisotropy energy that dictates how well you can stabilize the magnetic moments at a finite temperature. If the value is very small, what can happen, any thermal fluctuation can kill it. So you need a sizable amount of magnetic anisotropy.
Okay, let us thank Professor Biplab Sanyal for nice talk.